Hello, students. If you're watching this video, you've been watching writing out Lewis dot structures and using formal charge to pick the preferred Lewis dot structure. So in this particular video, we're going to go through steps 4 and step 5 to determine the preferred Lewis dot structure for dinitrogen oxide. So the first thing is, as always, you want to count your total valence electrons. So there's 2 nitrogen, right? Each nitrogen's group 5, so 5 valence electrons plus 6. I have a total of 16 valence electrons. So a lot of students miss this problem right off the bat because they assume because there's one oxygen that it's a central atom, and that is a bad assumption. If you look at the second rule, after we figure out total valence electrons, you need to determine the central atom, not based on the number of atoms, but based on the one furthest away from fluorine, or the more electropositive. So nitrogen is further away from fluorine. So nitrogen is actually my central atom. So I would bind, you would bind 1 oxygen and 1 nitrogen, and that takes up 4 electrons. So I have 12 electrons left. So then I would add those to the outer atoms to satisfy their octets. But when I look at this, I see from this structure that I'm not done, that I'm going to have to move these lone pairs and form multiple bonds. Remember, that's step 3. If the central atom doesn't have an octet, you move lone pairs to as a multiple bond. So there's 3 possibilities, okay? So 3 possibilities. There's possibility number 1, right? Possibility number 2. Possibility 3. So if I took just 1 lone pair from each outer atom and formed double bonds, I would have number 1. If I decided to take 2 lone pairs from the nitrogen, the outer atom of nitrogen, and attach those as multiple bonds, I'd have number 2. Or if I had instead would take the 2 lone pairs and take it from the oxygen and leave the single bond for nitrogen, I'd have 3. So which of these is the preferred structure? Well, that's why we got to follow these set rules. So if I look, formal charges, every single one of these nitrogens has 4 bonds. So you're not going to use that to determine which is the preferred structure. But we should figure out what the nitrogen, the central atom, so we'll call that nitrogen type A. So all of these have 4 bonds. So really, I'm going to give them all the same name. So the formal charge for nitrogen A is what? Again, total valence electrons, 5, minus number of bonds, 4, minus the number of electrons in lone pairs, 0, equals, whoops, I just put a 0, my bad, equals a positive 1. So every single one of the central atoms of these 3 possible Lewis structures, the nitrogen has a formal charge of +1. So now I have to go to the individual drawings. So if I look at this particular nitrogen, okay, I'll call this nitrogen B, okay, and I look at this particular oxygen, I'll call that oxygen A, okay, oxygen A. Let's figure out the formal charges of this particular species. So nitrogen B, 5 valence electrons, minus 2 bonds, minus what? 4 electrons in lone pairs gives me a -1 formal charge. So then we said that this was +1. This is -1. And you may remember oxygen likes to have 2 bonds, 2 lone pairs, so you're probably getting better. 6 minus 2 for the 2 bonds, minus 4 for the electrons and lone pairs is 0, 0. So we see that the +1 and the -1 kind of cancel each other out. Okay. So then we go over to number 2, right? So we've already calculated the central atom. So let's call this nitrogen C, and we'll call this oxygen B. And Nitrogen C, it has 5 valence electrons. It has 1, 2, 3 bonds and 1, 2 electrons in lone pairs. It has a 0 formal charge. Okay. And then I go to this oxygen. We've done this one before with the carbonate. It has 6 valence electrons. It has 1 bond, and then it has 6 electrons based on no lone pairs. So it has a -1. So just like this particular structure, number 1, number 2, we see that it cancels out to 0 as well because dinitrogen oxide is neutral. But let's go to this one. So I'm going to call this nitrogen D and this oxygen C. So if I go to nitrogen D and oxygen C, nitrogen D has 5 valence electrons, 1 bond, and 6 electrons in lone pairs. That ends up giving me a what? That's weird. That gives me a -2 because 5 minus 1 minus 6, basically 5 minus 7, it's a -2. So this has a -2. And then if I go to the oxygen, remember it hates 3 bonds because it has 6 valence electrons, minus 3 bonds, minus 1 lone pair gives me 2. That was a +1. And it hated being +1 because it's electronegative. So right off the bat, using step 4, I can illuminate the Lewis dot structure number 3 for dinitrogen oxide. Why? Because I want to have the lowest magnitude of formal charges. This has a magnitude of 2. None of these other ones have a magnitude of 2. It also has a formal charge on every single atom. Some of these have a formal charge of 0 on some atoms. So what am I going to do? I'm going to eliminate that one. So now how do I determine whether it's number 1 or 2? Well, that's the next rule. The next rule, rule number 5, asks, when the magnitudes of 2 different structures are the same, pick the structure where the negative formal charge is on the more electronegative element. So the magnitudes for 1 and 2 are the same. The central atom has a +1, and then one of the outer atoms has a 0, and then another outer atom has a -1. So the magnitudes are the same. So what do? We pick the structure where the negative formal charge is on the more electronegative element. So here on number 2, the oxygen carries the -1 formal charge. And on structure number 1, the nitrogen carries the -1 formal charge. So which one's more electronegative? Oxygen. It's closer to fluorine. So the preferred structure is number 2, because we want the oxygen to carry the -1 formal charge. So our preferred Lewis structure, I'll write it up clean, is this, with the oxygen having 1 bond carrying a -1 formal charge, and the nitrogen having 3 bonds, 1 lone pair, its preferred state, and a formal charge of 0. So I hope this video helps you with step 5, and yeah, stay tuned for step 6.